Hey guys, welcome to the first lesson of this unit. In this unit, we're going to be talking about chemical equations, balancing chemical equations. We're taking the next step from where we've been. So you recall that where we've been is talking about single compounds, nomenclature and how to name them, different things like that. Now we're going to start to get into actually doing some chemistry. So what happens when I take one compound and another compound and I mix them together and get something new. Okay, so we've been kind of setting the stage for this up to this point, but now we're gonna actually go there now. Okay, so for this first lesson, we're just gonna start with a shorter video. We're gonna talk about chemical equations. And before we jump into that, balancing them, I'm going to talk about how to construct them, and then we'll talk about how to balance them and the different kinds of equations that we'll run into, okay? So basically, what a chemical equation is just showing how two chemicals combine and make new chemicals, okay? And so we're going to have two parts of our chemical equation. On the first part, we're going to have the reactants. Okay, so that's going to go here on the left side. And then on this side, we're going to have our products. Okay, and what these are is our reactants are basically just the chemicals that we're going to start with. Okay, so let's start with a chemical equation here. Let's do nitrogen gas and hydrogen gas. Okay, so here's two chemicals I have. We know that N stands for nitrogen, H is hydrogen. The subscript 2 tells me that I have 2 of each of those atoms. Okay, and they're going to react together, and the atoms in these two chemicals are gonna recombine and make new chemicals. Okay, so they start on the left, and then on the right side are the products. Okay, and excuse me, these are the chemicals that are made in this reaction. So actually in this particular reaction, we have one product, ammonia, okay? And so we have our reactants and our products, and then in between we put an arrow to show the direction of the chemical reaction. And kind of the phrase we use here is we say yields, is kind of what this arrow stands for. So I would say nitrogen gas plus hydrogen gas yields ammonia. Okay, so this is going to be our basic structure for a chemical equation, okay, with our reactants on one side, products on the other side, and our arrow in the middle. Okay, so this is all good and well, but we'll notice something here is if I count the atoms on each side, I notice that something is not right here. So for example, if I look at my nitrogen on this side, this is my nitrogen gas, I have 2 atoms of nitrogen over here. But then when I do my chemical reaction, I end up with 1 nitrogen atom. Okay, so that doesn't seem right. And then similarly with my hydrogen, if I look here, I have 2 hydrogen atoms, but then somehow over here I ended up with 3. Okay, and we know that from the law of the conservation of matter, right? Matter cannot be created nor destroyed, right? In a chemical reaction, we're not creating new matter. We're not creating new atoms. We're just rearranging them in different combinations. Okay, so if I start with 2 nitrogens over here, I have to end with 2 over here. Or whatever, if I have more than 2 of either one of these or less, the numbers on each side have to be the same. Okay, and so that's what we mean by balancing a chemical equation. I'll just put balancing here. So that's going to be the next thing we do. So what we want to do is show how the chemical equations are balanced. Okay, I'm going to pull out a red marker to show this. We can do this by indicating the number of each molecule we have interacting in this reaction. Okay, so similar to mathematics, we talk about coefficients. These chemicals in this reaction can have a coefficient, okay? And so that's going to be some number. There's my marker. a coefficient is going to be some number that's going to go in front of each compound that I have here, okay? So what I want to do is I want to figure out which numbers I need to put here to make this equation balanced. Okay, and I'll kind of walk through this one and just kind of show you. So I notice if I have 2 nitrogens over here, I need 2 on this side. So I'm just going to start by putting a 2 out front here. And what this 2 is telling me is now I'm saying that I have made 2 entire ammonia molecules. Okay, so if I have 2 ammonia molecules, oh, this marker's not working very well here. Let me grab a green one, see if that one's any better. That's a little better. Okay, so if I have 2 ammonia molecules, I'll change this to green as well. I can see the total number of atoms I have. So if I have 2 ammonias, I have 2 nitrogens, but then I also have a total of 6 hydrogens. So I'm saying that in this reaction I've made 2 nitrogens in my ammonia and then 6 hydrogens. If I have 6 hydrogens on this side, well then I need to come back over here and change this coefficient so that I have the same number of atoms, hydrogen atoms on this side. Well, I can see that I have 2 hydrogen atoms per molecule, and I need to have 6 in total. So if I put 3 in front of there, now what we should have is a balanced equation, okay? And I can double check that. Here, let me erase down here. No, it's not erasing very well. Okay, so what I'm saying is I've started with, I have 1 nitrogen molecule, 3 hydrogen molecules, and 2 ammonia molecules is how this reaction is going, okay? And I want to double check to make sure it's balanced. Okay, so I'm going to say over here, I'm going to make a little table. I have 2 nitrogens. I have 3 hydrogen molecules, so that would mean I have a total of 6 hydrogen atoms. So these are all my reactant atoms. And then over here, I need to make sure I have the same amount, right? If I have 2 ammonias, that means I have 2 times my nitrogens. So my nitrogen atoms are balanced. I have 2 here and 2 here, so that's good. And then with my 2 ammonias, I should also have a total of 6 hydrogens. Okay, so now we can see I have the same number of nitrogens on this side, same on this side, and then same number of hydrogens on the left and the right. So now we can say that this chemical equation is balanced. I have not destroyed any atoms, I've not created any new ones, I've simply rearranged them into a new combination where I've had 2 gases and then now I have just 1 product over here of ammonia, okay? So that's kind of the general idea of where we're headed. Let's try another one, just to get some more practice with this. Okay, let's do another equation. Okay, so let's say I have methane reacting with. Well, let me put this over here. Scoot it over. So my reactants are methane and oxygen. Got to put my plus sign. Yields. Let me take a look here. Carbon dioxide and water. Okay, so here is a chemical equation. I have 2 reactants, and this time I have 2 products. Okay, there's no really rule on how many products or reactants we can have on either side. As long as it's something that actually happens, then this is how we can represent it, okay? So I can see this reaction taking place, and I want to now make sure that it's balanced, okay? And again, the only way I can balance it is by changing the coefficients in front of my molecules here, right? If I change the subscripts, that's changing what type of molecules I have. So I can't do that because then that would be a different kind of reaction. So so these are the 4 coefficients we need to make sure are correct. Okay, so a good strategy for this one's a little more complex, is I want to typically start with carbon or oxygen first. Hydrogen is a good one to do last. So how about we just start with carbon? So if I look on this side, as things are set the way they are now, I have 1 carbon atom. Okay, and if I look on this side, I can see that I also have 1 carbon atom. Okay, so my carbon is already balanced, so we're good there. Just gonna make a note of that. So let's move on to oxygen. Okay, on my reactant side, I have 2 oxygens, atoms that is, 2 atoms. On this side, I can see that I have 3. 1, 2, 3. Okay, so I want to think about how I can cause this one to be balanced. One strategy I'm thinking is that on this side we have an even number, and so on this side I also need an even number. Okay, this 1 oxygen by itself is kind of throwing things off. So let me put a 2 here just to make sure to see if that will work. So if I put a 2 on this side, that means I have, here, let me make a table. I've got 1 carbon, and then here, now I have 1, 2, 3, 4 oxygens, if I do it this way. 4 oxygens. So if I want to come back over here and make 4 oxygens, I would need a 2 in front of this one. And that would give me 4. Okay, so this process is just kind of trial and error of making sure everything works together. Okay, so I've got my carbons balanced, I've got my oxygens balanced, so now let's try our hydrogens. Let's take a look at what we have here. Actually, this might already be balanced. I've got 4 on this side, right? That subscript 4 tells me that I have 4 hydrogens on my reactant side. On my product side, I actually have 4 hydrogens as well, right? Because I take 2 water molecules. Each water molecule has 2 hydrogens. So this side also has 4. And then so with that, our chemical equation is balanced. So if these ones are left blank, it's just implied that there's 1 there, right? I don't need to write 1. We just leave it blank, and that implies that there's 1 of that molecule, okay? So this equation would be CH4 plus 2O2 yields CO2 plus 2H2O, okay? And so that would be how we balance that reaction. Okay, so we've gotten a bit of a start with chemical equations. We've kind of got an introduction to how to balance them. We're going to move on to a couple of other types of equations that we'll run into and talk about how to balance them. Okay, so we're going to talk about 2 of them here. I'm just going to make a note here on the side. The first type of equation we're going to talk about is a single replacement equation. And then we're going to also talk about, I misspelled that, double replacement reaction. Okay, let's start with this one. Okay, so we'll do a single replacement reaction. An example of that would be zinc plus copper 2 chloride yields zinc chloride plus copper. Okay, so this is an example of a single replacement reaction. Okay, and the reasons it's called that is because on my reactant side, I have a pure metal, a pure element, and then an ionic compound. So I'll just make a note, pure ionic, right? Copper 2 plus is my cation, Cl minus are my anions. I have 2 of them to balance this one. And we can see that on this side, now zinc is part of the ionic compound, and copper has gone to be a pure element. Okay, so we call this a single replacement reaction because the cation on the chlorides has been replaced with a different metal. First we started with copper, and then the cation is replaced with zinc, so that we have zinc chloride on this side, and then we're left with a pure metal left over. Okay, so that's the general idea of how a single replacement reaction is going to look. I start with a pure element and an ionic compound, and then they react, and I get a new ionic compound and a different pure element from what I started with. If I wanted to balance it and think about what coefficients I need to go in front here, it looks like it's actually already balanced. So some of these actually are pretty easy because you don't have to do anything, right? Let's double check. So here I'm going to make my table, zinc, copper, chlorine, and then I have my products on this side, copper, chlorine. Starting out, I have 1 zinc, 1 copper, 2 chlorines on this side. On this side, I also have 1 zinc, I have 1 copper, and I have 2 chlorines. So this one's already balanced. So all of these are just going to have coefficients of 1, and I really don't need to do anything. So that's an example of a single replacement reaction, but we don't need to do anything more to balance it. Okay, so let's talk about a different one that we actually need to do a little more work in order to balance. Okay, let's do another one here, another single replacement. I'm going to do sodium chloride plus fluorine gas yields, what do I have? I'm looking at my notes. Sodium fluoride plus chlorine gas. Okay, so we can see this is a single replacement because I have the cation on chlorine is sodium on this side, and then after, oh, did I write this wrong? Oh, no, it's fine. I'm sorry, the anion, so this one's an anion replacement. The anion has been replaced by chlorine, so sodium stays here, but we've replaced chlorine with fluorine. Sorry, I got a little confused there. Okay, so that's our single replacement, okay? And then this is our pure element, right? We just have pure fluorine gas, and then over here we make pure chlorine gas, okay? So let's take a look at balancing this one. I recommend making a table on each side to keep track of everything. Let's start with sodium. So here I have 1. On this side, I also have 1, so that works out pretty well. Chlorine, I have 1 on the reactant side. Oh, on the product side, I have 2 chlorine atoms, right? I have 1 molecule, but 2 atoms. Okay, so this is not balanced. So what I need to do is I need to change one of the coefficients in order to balance my chlorine atoms. Okay, I have 2 on this side. I think an easy thing to do would be to put 2 sodium atoms, or I'm sorry, sodium chloride molecules on this side. So that way I have 2 chlorines on this side and 2 chlorines on this side. Notice though that because I've put a 2 in front of this one, I've now changed the number of sodium atoms I have. Okay, so let's go back here and fix our sodium. So now sodium is 2. On this side, we still have 1 sodium. So now I probably need to put a 2 in front of this one to give me 2 sodium atoms. Okay, so now sodium and chlorine should be balanced. On this side I have 2 sodiums, this side I have 2 sodiums, I have 2 chlorines here because of the 2 coefficient, and I have 2 chlorines on this side because of that subscript. Okay, so now let's take a look at fluorine. On this side I have 2, and on this side I also have 2. So that coefficient right there means I have 2 fluorines on this side. So that actually worked out. By just taking care of my sodium and chlorine, I ended up taking care of the fluorine as well. Okay, so that's an example of balancing single replacement chemical equations. These ones are typically pretty straightforward. Now let's move on to double replacement and talk about those. Okay, so now we're gonna do double replacement chemical reactions. Let me get something written out here. So for our first one, we're going to do sodium sulfide plus hydrochloric acid, HCl, is going to give us, I believe it's sodium chloride, I'm looking at my notes, sodium chloride plus H2S, dihydrogen sulfide, monosulfide, that is. Okay, so here's our chemical equation. I've got my reactants, yields, my products, and now we want to make sure that it's balanced. Okay. Oh, actually, let me explain. So double replacement. So we can see that none of my reactants or products are pure elements, right? I have different atoms in each compound that I'm looking at. Okay. And what we're going to see is that I'm going to replace one of the partners, so to speak, in each one in this reaction, right? So I can see that my sodium, I'm replacing sulfur with chlorine. And then in a similar sense, here on hydrogen, I'm replacing chlorine with sulfur, okay? So both compounds are experiencing a replacement in this reaction, okay? So we have a double replacement, okay? So this one will be slightly more complicated to balance, but really not that much. Okay, so let's take a look here. Okay, so I'm gonna think about which coefficients I need to change. Let's set up our table here so we can keep track of the number of atoms on each side. Okay, so a good way to start is, at this point, all of the atoms are typically pretty different, so I would just pick one. Let's just start with sodium to begin with. So if I look at this side, I can see that I have 2 sodium atoms here. If I come over to my products, I only have 1 sodium over here. So the best way to fix that to begin with is putting a 2 out front there. So now I'm saying that I'm making 2 salts there. That gives me 2 sodiums. So my sodiums are balanced. Let's move on to sulfur. On this side I have just 1. On this side I also have just 1, so that works out pretty well. I've got that one taken care of. Now let's move to hydrogen. On this side I have 1. On this side I have 2. So in a similar case, if I have too many on this side, it's easier for me to put a coefficient on this side. So I'm going to put a 2 in front of this and change this here. So now that I have 2 hydrogens and 2 hydrogens on each side like that. Okay, now let's take out our chlorines, and they should also be balanced. I have 2 chlorines here, and I have 2 chlorines on this side as well. Okay. 2 sodium, 1, 2, 2. Everything is balanced now, I believe. Okay, so my coefficients are going to be 1, 2, 2, and just 1. Okay, so that's an idea of balancing double replacement reactions. Okay, let's do one more, and then we'll call it quits for this lesson. Okay, I'm going to throw in one with polyatomic ions just so we get some practice with that. Which one do I want to do? I'm going to go ahead and do this one, potassium hydroxide. Okay, you recognize that this is a polyatomic ion, hydroxide, plus aluminum nitrate. Yields potassium nitrate plus aluminum hydroxide. Ooh, that one's a little squished there, made it fit. Okay. So again, I can see this is a double replacement reaction because if I look here, potassium, his partner is getting switched from hydroxide to nitrate, and then the partner on aluminum, nitrate, is being replaced with hydroxide. Okay, so I have a double replacement reaction going on. Let's try to balance it. So I want to think about what coefficients I have. Now here's a trick, a good tip for balancing equations with polyatomic ions. Okay, it can be tempting in making my table to try to set this up for individual elements. Okay, the thing is, it's going to get confusing, particularly with oxygen. I have oxygen in my hydroxide, but I also have oxygen in my nitrate. Okay, so that one might be a little complex. One thing that's important to note is that in doing this reaction, hydroxide stays as one unit, right? And this hydrogen and this oxygen don't split up from each other. Okay, when I come over here, I still have hydroxide as one complete piece. Okay, same thing with nitrate. We can think of this as one puzzle piece that doesn't break apart from itself during the reaction. So in balancing this, what I recommend, instead of doing it by elements, I recommend having polyatomic ions on their own category. So we'll do potassium because it acts as one piece, aluminum, hydroxide, and then nitrate, like that. And so in balancing it, I'm going to think of these as singular puzzle pieces that are moving around and being recombined in my reaction. Okay, so let's try this. So let's start with potassium. On the left side, I have one potassium atom. On this side, I have one potassium. Okay, so that one's actually balanced. That's not too bad. Coming back over here, let's move to the next one. Okay, so I'm not doing oxygen, I'm doing hydroxide. I'm doing the whole thing as if it were one puzzle piece. Okay, so I want to ask myself, how many hydroxides do I have on this side? Just one. On this side, I have 3, right? This subscript 3 outside the parentheses tells me that I have 3 hydroxide ions there, okay? So I'm going to put a 3 there. Okay, so this is not balanced. I have 3 hydroxides on this side and 1 on this side. Okay, so what I recommend is taking the smaller one and changing that coefficient to match. So now on this side, if I put a 3 there, I should end up with 3 hydroxides to match these 3 hydroxides. Okay, now recall, if I put a 3 here, I'm also changing my potassium. Now on here, I have 3 potassiums, so I got to change that. Let's come back over here. I have 3 on, or I need 3 on this side to match, and I only have 1, so let's also put a 3 in front of this compound. Okay, so now I have 3 potassiums and 3 hydroxides on both sides to match. So now let's move on to the next element. I've got aluminum. On this side I have 1. If I come over here, I also have one, so that one's balanced. Let's move to nitrate. Again, I'm going to think of this as one puzzle piece. So I have 3 nitrates on this side because of this 3 here. And then if I come over here, it works out pretty nicely because I actually have 3 on this side, right? 1 nitrate by itself, but this 3 coefficient causes me to have 3 nitrates, right? The coefficient does that for me. So now I can see that everything is balanced. Okay, so that's an example of double replacement reactions with polyatomic ions. So I recommend that when we're trying to balance anything with a polyatomic ion, make sure that you treat the polyatomic ion as one unit instead of splitting it up. That will make things a lot easier and a lot more straightforward when you're balancing these reactions. Okay, well, that does it for this first lesson. Go ahead and try some of the practice problems, and I will see you in the next one.